the smallest component of the element. Everything surrounds us either in the form of solid, liquid, gas or plasma is made up of atoms. Our body is made up of atoms. And do you know how many atoms are present in our body? Approximately there are 7 billion number of atoms present in our body, which is approximately billion times of overall human population of the earth. Myself, Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering, welcome you all in my second lecture of atomic structure. Atomic structure is included in the Module 1 of the chemistry syllabus of BTech course. The code for the paper is that either CH101 for odd semester or CH201 for even semester. And you know that already we discussed a Rutherford's model from the alpha ray scattering gold foil experiments, and then Rutherford established the atomic model. What was the model? The model was that maximum part of the atom vacant, and in the center there was some heavy dense nucleus exist. Electrons are revolving, but that model was unable to explain the stability and the atomic spectra. Then Niels Bohr came to the field, and Niels Bohr successfully explained the atomic stability and the spectra. But Niels Bohr model also have some kinds of limitations. So up to that point we discussed in the previous class. Now today what we'll discuss? Today we'll discuss that what are the applications of Niels Bohr. There are so many applications. Like from the Niels Bohr model or the Bohr's model, we can determine the radius of the Bohr orbit. We can determine the total energy of the electron in a particular orbit. We can determine several spectral parameters like wavelength, like frequency, like wave number, etc., etc. So that all the things we will determine today in today's class with some numerical problems, because there are so many numerical problems are also important from that topic. Then we'll discuss today that how Sommerfeld explained successfully the drawbacks of the Bohr's model, and also how Sommerfeld established a new model or modified the Bohr's model with a new quantum number. But Sommerfeld's model also have such kind of drawbacks. We'll also discuss today what are the drawbacks of the Sommerfeld's model. So all the topics we will discuss today. So without further delay, let's go to the class. First of all, we'll discuss about the application of the Bohr's model, and you know that from Bohr's model we can calculate there are some parameters like radius of the Bohr's orbit, the energy of the electrons. That parameters we can calculate from the Bohr's model. So first of all, radius. How we can calculate the radius of the Bohr's orbit? So generally we'll take it as the R. So R represent the radius of the Bohr's orbit. So for that purpose, look here, we already discussed that there are two types of forces which are acting in opposite direction. First one is that in inward direction there will be electrostatic attraction force or there will be centripetal force, and outward direction you know centrifugal force, and that two forces are same but in opposite direction, and that is the main reason behind the stability of the atom. So now what is the force of that inward direction, value of the force, or how we can express it? For example, we can take it that Z is the atomic number, and E is the charge of the either proton or the electron. Okay, so Z is the atomic number and E is the either charge of proton and electron. So according to Coulomb's law, we can write down Ze square, that means Ze into E for the electron, another electron. So here it is E and here it is the Ze. So Ze square by R square, it is the Coulomb's law, and this is the centripetal force. In another outward direction, you know that their centrifugal force is acting. What is the value? That V is the velocity of the electron. Here mv square by r, V is the velocity of the electron, and that's why here mv square r by r. So from that equation, that Ze square by r square equal to mv square by r, that are obviously equal, such that electron can continuously revolve around the nucleus. It is the first equation, and from that equation V square equal to Z square by R m. So here we can get one equation, and another equation also we know that mvr equal to nh by 2 pi. That already we discussed when we discussed about the postulates of the Bohr's model. So mvr equal to nh by 2 pi, and from that equation also we will get one equation, that v square equal to n square h square 4 pi square m square r square. So v square equal to n square h square 4 pi square divided by m square r square. So v square equal to n square h square 4 pi square m square, and here v square equal to Z square by r m. Okay. So both the equation, that v square equal to Z square by rm and v square equal to n square h square 4 pi square m square r square, with that equation then there will be equality between that two equations. That means Z square by rm equal to n square h square divided by 4 pi square m square r square. So from that two equation we can write down the expression of the radius. That means what will be the expression of the r. We'll get from that two equation, we'll get that r, that means the radius of the Bohr orbit. Bohr orbit means nth orbit. Okay, here r means equal to rn, that means the radius of the nth orbit, that equal to n square h square divided by 4 pi square m Z square, where n is the principal quantum number, you know, h is the Planck constant, and m is the mass of the electron. It is the mass of the electron, Z is the atomic number, and charge of the electrons. So that equation is very much important, but the main part which we have to keep in mind, that Rn, that equals to h square divided by 4 pi square m square into n square by z. So that part we have to keep in mind. Because that part, that almost constant. So Rn proportional to n square by z, that we have to keep in mind. That is very, very important. If we keep the value for hydrogen atom, in that case n equal to 1 and z equal to also 1. So if we put all the values for hydrogen atom, then what happened? R equals to 0.529 angstrom. So that is a standard value for hydrogen atom. Rn equals to RH into n square by z. Rn equals to RH into n square by z. So that is the main expression which we have to keep in mind for the numerical purpose, and mainly Rn proportional to n square by z, that also we have to keep in mind. I will give you one example also, that what type of question may arise from that portion. I will also give you that type of question. Okay, so if we try to make an order, that hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, so we have to make an order by which the radius of the hydrogen, helium plus, lithium 2 plus and barium 3 plus, we have to show the order, the increasing order. Okay, so for that purpose we know that R proportional to n square by z. So here for each and every case it is considered the first Bohr orbit. First Bohr orbit. So that means here n equal to 1. Obviously here n equal to 1. So here if n equal to 1, the remaining part are that proportional to 1 by z. With increasing the atomic number, the radius will be decreased. So that means it is the inversely proportional. So if it is inversely proportional, the radius will be higher for. If it is inversely proportional, the radius will be higher for hydrogen, then helium plus, then lithium 2 plus, then beryllium 3 plus. As the beryllium 3 plus has the highest Z value, that is the atomic number, so obviously that beryllium 3 plus will have the lower radius, as it is the inversely proportional. We will move to the second application of Bohr's model. According to the second application, we can determine the energy of an electron in a particular orbit. So that means when one electron revolves in a particular orbit, we can calculate what will be the energy of that particular electron when it is in a particular orbit. So now how we can calculate that energy value? You know, energy means any kind of energy, that means it is the summation of the kinetic energy plus potential energy. Now kinetic energy, all of we very much know very well, we know very well that kinetic energy equal to half mv square. Now potential energy equal to z square by r. How it is possible? How we can determine the potential energy? So potential energy we can determine by that way that potential energy equals to, it is the integration of z square by r square, that infinity to r. That means potential energy can be determined by that way that it is the work done from to bring the electron from infinity distance to a distance r from the nucleus. So that's why it is the integration of infinity to r z square by r square. We already discussed about that z square by r square, how we got that equation. Now the integration of that equation, that will be z minus z square by r, and that's why it is the value of potential energy. Now what will be the value of half mv square? We already established the equation that mv square by r, that equals to z square by r square. We already discussed that mv square by r equal to z square by r square. So from there we can write down half mv square by r, that equals to z square by 2r square. Then it will be cancelled out. So half mv square equals to z square by 2r square. So it is the value of half mv square. So from here we can get the value of half mv square. Now here we will put the value of half mv square. So it will be z square by 2r square minus z square by r. So z square by 2r square minus z square by r, and what will be the result? Minus z square by 2r minus z square by 2r. Okay, now we will put the value of r. We already calculated that what is the expression of r. We already calculated the expression of r. Now here just we will put here the value or the expression of the r, and that will be minus z square by 2 into 4 pi square z m square divided by n square h square. So now finally what we'll get from that equation that energy equals to 2 pi square m z square e to the power 4 divided by n square h square. So this is the final expression for the energy of an electron which when the electron is in a particular orbit. So finally we'll get that equation, energy equal to minus 2 pi square m z square e to the power 4 by n square h square. Now from like the previous case also, here if you check that all the terms that are almost constant. So we can write down E proportional to, or E equals to minus E of hydrogen into z square by n square, or we can write down E proportional to z square divided by n square. That means that in case of hydrogen, when we will take that z equal to 1, and if we consider that principal quantum number 1, that is the first orbit of the Bohr model, or the Bohr first orbit, then n equal to 1. So then we will get that it will be equal to EH. And what is the value of EH? You know, EH equal to minus 13.6 electrovolt. Okay. So if EH equal to minus 13.6 electrovolts, obviously here minus sign will not be, because that 13.6 will come considering the minus sign also. So E equals to simply EH into z square by n square, or E proportional to z square by n square. So now if there is such kind of question that you have to compare the energy of the electrons for different one electron systems, then simply you have to consider, you have to simply keep in mind that relationship. I can give you one example also. Like the previous case, here you have to compare the energy of the first Bohr orbit in case of hydrogen, helium plus, lithium 2 plus, and beryllium 3 plus. Okay, so students, what you have to do, just pause the video here and you have to solve the problem, then you will see the next part. Okay, otherwise there will be no scope of practice of in your case. So that's why it's my request to all of my students that please pause the video here and try to solve that what will be the order of either increasing order or decreasing order of the energy of first Bohr orbit for that 4 cases. Okay, so I think all of you have done, or you have solved the problem. Okay, so then check either it is right or wrong. Okay, I am discussing what will be the solution of that problem. I told you that you have to compare the energy order of the first Bohr orbit. So according to that equation, if we consider the first Bohr orbits of each and every case, here n equal to 1. So each and every case here n equal to 1. But z will not be 1. Here z equal to 1, 2, 3, 4. What I told you, that z is the atomic number. So if z is the atomic number, then obviously it will vary from hydrogen, helium, lithium, beryllium. So now the equation reduces to that equation reduces to E proportional to z square. So if it E proportional to z square, then obviously if z will be increased, then the energy value obviously increased. So the order will be like that. Okay, so the order of the electron in first Bohr orbit will be highest for beryllium 3 plus, then lithium 2 plus, then helium plus, then hydrogen. So that's a very important question you have to keep in mind. Like in case of radius also you have to keep in mind. The question may asked in that way, and you have to compare the order of the radius. Here also the question may asked in that way, that you have to determine the order of the energy also. So for that purpose you have to keep in mind that equation. Now from the next part, that what is the significance of the negative sign in the energy expression. That is also very important question. Like we discussed about that for hydrogen atom, E is equal to minus 13.6 electrovolt. Okay, so now what is the significance of the minus sign? That is very, very important. Okay, what is the significance of minus sign? So now think about that fact that if it is the nucleus and if it is a particular orbit and it is the electron, so electron is revolving here. So that means electron is more stable here than the outside of the atom. So electron is more stable in the atom than the outside of the atom. That means you have to apply, or we have to apply the energy, to remove the electron from the atom. So that is the significance of the negative sign. That means when we have to apply the energy to an atom, that is taken as a negative sign. If we get the energy from the atom, that means if energy coming out from the atom, then it is taken as the positive sign. So here you have to apply the energy if you want to remove, or if we want to remove the electron from any orbit of the atom. So that's why here negative sign. That means negative sign indicate electron is more stable in a particular orbit than the outside of the orbit. So that is the inner meaning of the negative sign of the electron. That is the significance of the negative sign in the energy expression of the electron. We can also determine some kinds of parameter. Parameters means like lambda, like nu, bar. What is the meaning of that? Each and every sign. Lambda means it is the wavelength. It is the wavelength, and nu means it is the frequency. Nu means it is the frequency, and nu bar means it is the wave number. Wavelength means if it is the wave, okay, so the distance between that two peak, that is called actually lambda. So it is the lambda, the distance between two peaks, that is called actually lambda, and it will be the unit of distance obviously. For example, it may be centimeter, maybe meter, maybe nanometer, maybe picometer, okay. So that, or maybe angstrom also. So that may be all the unit of the distances. So that is called actually lambda, or the wavelength. Now what is the nu? Nu is the frequency. So first of all, this is the complete cycle, okay. This is the complete cycle. So the frequency means the number of complete cycle per second. That is called actually frequency. So frequency can be defined in that way, number of complete cycle per second. So the unit of the frequency, that will be hertz, okay. So it is the unit of the frequency. What is the wave number? Wave number means number of complete cycle but per unit distance, okay. That means in the previous case it was the per unit time or per unit second, whatever. Here it is the per unit distance. That means what will be the nu bar? Unit of the nu bar, it may be centimeter inverse, it may be meter inverse, it may be nanometer inverse, etc., etc. So that will be the unit of the nu bar. Okay. And each and every term, they are also interrelated. Like all of you know very well that E is equal to h nu. All of you know very well. Then nu is equal to c by lambda. Nu is equal to c by lambda. Again, lambda is equal to 1 by nu bar. 1 by nu bar. Now what is the c? C is the velocity of light. Velocity of light. Okay. So by that three equations we can interrelate with each other. That means if we know any of the parameter, like if you know lambda, if you know frequency, if you know nu bar, whatever, we can convert one value to another value by that three equations. So that three equations are very much important to relate each other. Now if one electron jump from the higher orbit to lower orbit, that means we already discussed about that with increasing the principal quantum number, the energy of the orbit increases in that order, K, L, M, N, like that. So for example, if any, this is the E2, E2 means it is the higher energy orbit, and it is the E1. Okay, so it is the energy of the higher orbit, it is the energy of the lower orbit. So whatever, if one electron jump from the E2 to E1, then it obviously it have to, or it has to emit the energy. That means the electron must release some energy when it jump from the higher orbit to lower orbit. According to Bohr's model, what we calculated, that energy expression equal to minus 2 pi square m z square to the power 4 by n square h square. And now here, look here, if it is the E2, for example, if we take that N2 is the corresponding orbit for the E2 and N1 is the corresponding orbit for the E1, then what happened? And look here, then we can write down in that way that for E2 that is the energy expression, and for E1 that is the another energy expression. Now from there we can, from here we can write down that what is the common term, that h nu equals to, we can write down here the common term, that is the 2 pi square m z square e to the power 4 divided by h square, then it equals to 1 by n1 square as minus minus plus, and then minus 1 by n2 square. So we can write down that expression simply. So what is the common factor here? That common factor, it is constant. Okay, so it is actually constant. Then again we can write down that nu is equal to, it is actually h nu, so nu is equal to it will be 2 pi square m z square e to the power 4 by h a cube, and that area will be same, n1 square minus 1 by n2 square. Then we know that nu bar is equal to nu by c. So we can write down, if we write down here the value of the nu, then the equation will be 2 pi square m z square e to the power 4 by c h a cube 1 by n1 square minus 1 by n2 square. Now look here, in that equation here, 2 pi square m z square e to the power 4, it is a constant, and that constant is called a Rydberg constant. A Rydberg constant. Okay, so in that Rydberg constant, look here, if you take that equation for the hydrogen atom, then what happened for z value? Z equals to, it will be 1, z equals to 1. So we can write down that equation reduces to nu bar is equal to, if it is the constant, then it will be constant for hydrogen, and then z square, as the atomic number of hydrogen will be 1, so obviously it will be, you have to consider the z square if you apply the Ra, or if you consider normally R, then it's okay, R into the other side of the equation. So 1 by n1 square minus 1 by n2 square. So look here, the what is the nu bar? Nu bar is the it is actually wave number, and I told you that if you know any one parameter, like if you know the frequency, if you know the lambda, if you know the nu bar, if you know the E, then you can calculate any other parameter, because they each and every parameter, they are interrelated with each other. So here we consider nu bar. Nu bar actually it is the wave number of the radiation. What is the radiation? Radiation means which radiation is coming out from the atom when one electron jump from higher to lower orbit. So now this equation, that it is the final expression, and you have to keep in mind, because that is very very important for the to understand the spectral nature of the atom, or the spectral characteristics of the atom. Here also the value of RH, that means the Rydberg constant, that equals at 109677 centimeter inverse. That is the value of the Rydberg constant, and you have to keep in mind that value that may be important for the normally it will be reflected in the question because generally it is available in the question also, but you can keep in mind also. But you have to keep in mind that equation because that equation we have to use in the next topic also. From there we can find out that there are some spectral series of the hydrogen atom and particular name of that series also, and we will determine from that equation. So there are some particular series, that means if for hydrogen atom, if we consider N1 equals to 1 and N2 equals to, it may be 2, 3, 4, etc. That means any of the higher orbit, maybe 2, 3, 4, etc., etc. If the electron jump to the first orbit, that means the N1 equal to 1, that means the principal quantum number equal to 1, then what happens? Then obviously what series will get, that is called Lyman series. That is the Lyman series. Okay. Next one, if N2 equal to, if N1 equals to 2 and N2 equals to 3, 4, 5, etc., etc. That means any of the higher orbit with respect to 2, if electron jump here, then what series we obtain, that is called the Balmer series. Balmer. Okay. Next one, if N1 equals to 3 and N2 equals to 4, 5, etc., then it is called Lyman, Balmer, then Passon. Okay. Next one, if N1 equals to 4 and N2 equals to 5, 6, etc., then it is called bracket series. Okay. Then if N1 equals to 5 and N2 equals to 6, 7, etc., then it is called P-formed or formed, whatever. It is called P-formed. If N1 equal to 6 and N2 equals to 7, 8, etc., then the series called Humphreys. Okay, so that are the table which you have to keep in mind, because there may be some kind of question also. I'll give you some assignment also, such kind of, where you have to find out that the spectral line which is generated from the hydrogen from any of the jump of the electron, maybe 2 to 1 or 3 to 2 or like that, you have to find out. Then you have to tell that that spectral line fall in which series actually. Okay, that you have to find out, or you have to write down. So that's why that table you have to keep in mind: Lyman, Balmer, Passon, bracket, and the Humphreys. Okay, that is very, very important. Okay, now we'll discuss about the solution of the problem. So in the first problem, look there that it is given the energy of the first Bohr orbit, that is given. Okay, so we have to calculate the energy of the fifth Bohr orbit, and when we calculate when we determine the expression of the energy from the Bohr's model, there we discussed about that energy that very much proportional to the very much inversely proportional to the its principal quantum number. Okay, so if it is the first Bohr orbit, the principal quantum number will be 1. If it is the fifth energy level or fifth Bohr orbit, then obviously the principal quantum number will be 5. Now if E inversely proportional to the principal quantum number square, then what happened? Here we can write down E1 equals to, look here, 1 by 1 square, for it is the first energy associated with the first Bohr orbit. So obviously the n value will be 1. If E5, that means it is the fifth. Okay, if it is the fifth Bohr orbit, then obviously n equal to 5. So E5 inversely proportional to 5 square. Then what happened? If it is the 2, second equation, if it is the one equation, then if second divided by first, then what happened? Then E5 by E1 then equal to, if it is the E5 by E1, then 1 by 25. Okay, then here look, E5 equals to E1 by 25, then E1 value that is given in the question, that is given that at minus 2.17 into 10 to the power minus 18, then divided by 25, then obviously it will be minus 8.68 into 10 to the power minus 20 joule per atom. So just check your answer that either you did the right or wrong. Okay, just check the answer and the procedure. If you are unable to solve the answer, try to understand from here. You can take a screenshot also from that solution, then you can do, or you can write down in your copy. And one thing, students, it's my request to all of you that when you are attending my class, then what you have to do, you have to take one copy. When we'll solve some question answer or problems, or when we will discuss something, you have to make a note, okay, or you have to note down all that things. Okay, so now come to the second problem. In the second problem also there are something which you have to know. So first of all, look here, there are some things which is written the H alpha, H beta. First of all, you have to know that what is the H alpha and what is the H beta. H alpha means it is the first line. It may be any of the series. It may be Lyman, it may be Bohr, it may be Balmer, it may be Basson, etc., etc. But the first line will be H alpha for hydrogen case, and second line for H beta. So now if H alpha first line, and if it is the Balmer series, it is also mentioned in the question that if it is the Balmer series, then what happened? Then N1 equals to 2 and N2 equals to 3, because you know in case of Balmer series that the electron come from the 3 to 2. So then obviously you know that nu bar equals to, we already discussed that nu bar equals to 1 by lambda r. R is the Rydberg constant, the value of that Rydberg constant that is also given in the question. So then 1 by n1 square minus 1 by n2 square, and then you can, if you put the value of Rydberg constant, and it will be the 3 to 2. If it will be beta series, then it will be whatever, it will be 2 to 4. Okay, if it is asked in the question, then what is the H beta? Here it is not mentioned in the question, but if it is required, then you have to put there in 1 equal to 2 and in 2 equal to 4. So here 1 by 2 square minus 1 by 3 square, then you can find out if you know nu bar equal to 1 by lambda, then after calculation you can find out lambda equals to 6.565 in 10 to the power minus 5 centimeter. Okay, so we already discussed in the previous class that there are some drawbacks of the Bohr's model. That drawbacks actually was unable to explain, mainly from the experimental point of view. The Bohr's model was unable to explain the fine structure. What was the fine structure? Fine structure means each and every line of light spectrum, when it passed through a high resolving power spectrophotometer, then what happened? Each and every line will be split into the small lines. That small lines indicated that there must be some kinds of sub-energy level, but that was not explained by Niels Bohr, and that's why the next scientist came to the field, and he was Sommerfeld. So according to Sommerfeld, there was some kind of sub-energy level in the atom, and Sommerfeld introduced a new quantum number. Sommerfeld told that electron revolve surround the nucleus, not only the circular pathway. Actually, circular pathway is the some special case of elliptical pathway. So this all looks like ellipse. So the elliptical pathway actually the main pathway of the electron. But circular pathway, what Bohr told that circular pathway was the special case for any atom. So according to Sommerfeld, he introduced a new quantum number that is called azimuthal quantum number. Azimuthal quantum number. Why? Because by this azimuthal quantum number, Sommerfeld explained the existence of sub-energy level. According to Sommerfeld, that nuclei exist in the focus of the ellipse, and there are two things or two parameters which are changing, that is actually the angle, it is the phi, and that distance, radius. So when one electron revolves through that elliptical orbit, then the angle and the radius, that will be continuously changing. Okay, and that's why Sommerfeld introduced a new quantum number that is called azimuthal quantum number. And what is the significance of azimuthal quantum number? According to Sommerfeld, azimuthal quantum number later on azimuthal quantum number, that is denoted by the L, and for a particular value of n, or for a particular value of n, we know what is the n was the principal quantum number. So for a particular value of n, L will be 0 to n minus 1. That means, for example, if n equal to 2, L will be 0 and 1. Now think that if L is equal to 0 and 1, we already discussed that what is this meaning of the 2. 2 means it is a particular cell or the orbit that was named by the L. Okay, we already discussed for n equal to 1, that was the K, and for n equal to 2, that was the L. So for L, or for that particular energy level, if it is the one line, that means one line which is generated for that particular energy level, then it is expected that it will be splitted into the two lines, because that 0 and 1, they are the subcell of that particular cell. That means one line will be split into the two energy level. One line for one energy level will be split into the two sub energy level. So according to Sommerfeld, he introduced that for a particular value of, if L equal to 0, then the name of the subcell will be S. If L equal to 1, the name of the subcell will be P. If L is equal to 2, the name of the subcell will be D. And if L equal to 3, it will be F. So now S, P, D, F, that are corresponding to a particular value of the azimuthal quantum number. And actually this is the significance of azimuthal quantum number. So azimuthal quantum number signify that the existence of the subcell of in a particular atom, and this is the beauty of the Sommerfeld model. Sommerfeld first explained that there are some kinds of sub energy level or subcell in a particular atom, and by explaining the term azimuthal quantum number. N is equal to, if n is equal to 1, then L is equal to 0. That means if n is equal to 1 means it has the only one cell or one orbit, that is the K, and here also S. But if n is equal to 2, then obviously L is equal to 0 and 1. So that means if it is the L, it will be one for S and another for P. That means L, that is the combination of S and P. In the same way, if n is equal to 3, L will be 0, 1, 2. That means if 3 corresponding to M, and here S, P, D. That means M, that cell or that orbit, that is the combination of S, P and D. And if n is equal to 4, then n is equal to 0, 1, 2, 3. That means S, P, D and F. So here n, that is the combination of S, P, D, F. So that are the 4 subcell which exist in the N cell. That means one line is expected, one line that will be split into the so many small lines. Okay, so that is the Sommerfeld model, and the most beautiful thing of the Sommerfeld model explained successfully the fine structure of the atomic spectra. and obviously it explained, or it first told that there is some kind of existence of the subcell in an atom. Sommerfeld model also suffers from some limitations, like up to Sommerfeld model, it was considered that electron has the only particle nature. But further, know that electron has the dual character, both particle and the wave. But the wave nature of the electron was not explained by the Sommerfeld model. Second drawback, Sommerfeld model also considered the two-dimension figure or the two-dimension structure of the atom. But we know atomic structure actually three-dimensional. So it was also not explained by the Sommerfeld model. As the Sommerfeld model considered the particle nature of the electron, not the wave nature, it is unable to explain the Heisenberg uncertainty principle. So Sommerfeld model also, like the Bohr's model, unable to explain the Heisenberg uncertainty principle. There is another important drawback of the Sommerfeld model, like the Bohr's model also, that the fine structure of atomic spectra that was again splitted into small lines in presence of either magnetic field or electric field. That was not explained by the Sommerfeld model. Like if it is the fine structure, that fine structure again splitted either in presence of magnetic field or electric field into the small lines. If it is splitted into the small lines, that means like the same way how Sommerfeld thought, in the same way we can tell that there must be some existence of another energy levels, which was not explained by the Sommerfeld. So that is the another drawback, and that all the drawbacks will be removed by the another two scientists, Zeeman and Stark. We will discuss later what is the Zeeman effect and Stark effect. But these are the main important drawbacks of the Sommerfeld model. So students, now we will discuss about the assignment of the previous class, and I think all of you have completed your assignment. So just check the answers of what you have written in your copy. Either it is right or wrong. So come to the first question. What was the first question? The first question was, why atomic spectra is line spectra, not continuous one? So atomic spectra, that is obviously line spectra. Why it is not continuous spectrum? Continuous spectrum generated when light or energy continuously emitted from the source. Here source is the atom. Now according to Bohr's model, electrons will not emit the energy continuously. When one electron restricted in a particular atom, it neither emit the energy nor absorb the energy. That means we are not getting the energy continuously. So there is no question of getting the continuous spectrum. But when one electron jumps from the higher to lower orbit, then only it can emit the energy. So that means sometimes we may get the energy, sometimes not. And that is the concept of line spectrum. That's why we are getting the line spectrum from the atom, not the continuous one. On to the second question. What was the second question? The second question was, what is the significance of principal quantum number? Principal quantum number signify the existence of orbit. That means what equation proposed by the Niels Bohr, mvr equals to nh by 2 pi, that n principal quantum number denote the orbit of the atom. That means if n equal to 1, it will be k, if n equal to 2, it will be l, and so on. Now come to the third question. What was the third question? How Bohr modified the Rutherford's model. Actually, Rutherford's model was the main two drawbacks regarding stability and regarding atomic spectra. The stability of the atoms, it was successfully explained by the Niels Bohr by that way, when one electron continuously revolves around the nucleus in a particular orbit, it neither emits the energy nor absorbs the energy. That means there is no question of decreasing the outward force, that means centrifugal force. So if the outward force or the centrifugal force will not be decreased, it will remain same with the inward Coulombic attraction force. No question of the jumping of the electrons in the nucleus, so atom remain stable. And the second answer I already discussed a little bit in the first question, that if the atom do not emit the energy continuously, no question of getting the continuous spectrum. So obviously we will get the line spectrum, because when one electron jump from the higher to lower orbit, then only we can get the spectrum or the energy, otherwise not. So that means we should get the line spectrum, and actually or experimentally we get the line spectrum. The question was, what is the alpha particle? What is the alpha particle? Alpha particle is the helium nucleus, that if we remove the two electrons, then what is produced, that is called the alpha particle. Last question of the previous day assignment regarding light spectrum, what is the drawback of Bohr's model? That's simple. That light spectrum again split it in presence of high resolution spectrophotometer, and each and every line when split it indicates that there must be some sub energy level in a particular orbit, but Bohr's model was totally unable to explain this fact. So that's why the fine structure or the further splitting of the light spectrum with high resolution spectrophotometer was not explained by the Bohr's model. Okay, so that all the answers I already discussed with you. Just check either it is right or wrong. I know maximum of the students have done the answer rightly. If there is any mistake, just write down incorrectly. And now this is the today's assignment for you. Just you can, like the previous class, you can take a screenshot of that questions, and then you have to write down in the same way. That is also your home task. Write down the answers, and I will discuss with you the answers of the questions in the next class. So meet with you in the next class. Take care. Goodbye.